This is an example problem for Physics 1607, Auburn University, Fall 2013. So this is another example problem, or this is another problem, end of chapter problem from your textbook. And the idea is you're standing on a sheet of ice. So there's a frictionless surface here, and that's important. I'll explain that in a second. You're standing on a sheet of ice, and someone throws a baseball to you with a given mass at some speed v1. I'll call the mass of the baseball m1, and your mass is given. I'll call that m2. And then the problem asks you to characterize two different situations. The first one is you catch the ball, and it asks you what speed do you and the ball at what speed do you and the ball move after you catch it. So the first thing to talk about here is notation. If M1 is the ball here and M2 is you, I find it convenient to define something like a big M, which is the total mass 1 plus M2. You don't have to do it that way, of course. You can define it as anything you want to, but it makes the notation a little easier to handle. It's less cumbersome, so I like to do that. The second thing to notice, it's really important that this is a frictionless surface. What that means is that between you and the baseball, there are no outside forces that are acting. There's no non-conservative forces here. So what we can do very easily is apply conservation of momentum to this problem. And of course the conservation of momentum simply says that the momentum before this collision occurs is equal to the total momentum afterwards. And I should use the words total there. So at this point, it just becomes a simple matter of actually calculating what those quantities are. So the total momentum beforehand, we've got to add the momentum of the baseball, so that's going to be m1 times v1, plus the momentum of u, which is going to be m2, times whatever your velocity was. But of course, you're starting out from rest, and so this is going to be a zero term here, and this whole component goes to zero. I'm just including it for purposes of clarity because in general you might have some sort of initial velocity as the person, and so in general this term is not going to be zero. In this particular case it is, and that's all the momentum we have before you catch the ball. And after you catch the ball you have m1 v2 plus m2 v2, where we're noticing here that V2 is the same. In other words, you and the ball have the same momenta. You caught the ball, so clearly you have the same momenta. So I can just put this all together, M1 plus M2 times V2, and I've already defined M1 plus M2 as some big M V2. So that was just a couple of steps to show you where I'm going with it. I'm actually going to erase it to give myself some room. Of course, you can rewind the video to watch that if you need to. But the total momentum after the collision is just big M V2, for big M defined as we have up here. And V2 is actually what we're being asked to find. So it's really just simple algebra here. V2 is going to equal m1 v1, the total momentum before the collision, over big M. If you want me to unpack that, of course I can. m1 v1 over m1 plus m2. As long as you've defined m1 plus m2 as this big M, you can use either one of these notations. It doesn't bother me. And so that's done. That's the first part of the problem. The second part asks, what about the situation where you don't catch the ball? Afterwards, the ball is going to be moving with some V2 here, and in other words, it bounces off of you. And you're going to be moving with some V3 that way. So this, I should point out, this V2 is not the same V2 as in the previous part of the problem. It's a brand new V2, and now we have another velocity here, V3, and so this is M1 and we're still M2. So I'm just going to apply the conservation of momentum again. My total momentum before the collision is still m1 v1. Nothing's changed, and that just comes from noticing over here the only thing moving is the baseball. So m1 v1 is the total momentum. And afterwards, what I've got is the momentum of the baseball, but notice the direction now, and I'm given that that direction is the case, and so I'm going to have a negative here, m1 v2 plus m2 v3, and I believe what I'm being asked to find is yes, I'm still being asked to find v3. And in this part of the problem, v2 was actually given to me. It told me what the baseball was moving at. And so I'm still being asked to find my momentum. And so again, it's just basic algebra at this point. If you run it through, you're going to get an m1 times v1 plus v2 equals m2 v3. All I did was factor out the m1 after I moved this term to the left side of the equation. And so of course v3 is just m1 v1 plus v2 over m2. Now I'm not putting in numbers here because you guys can do that pretty easily, but what I should point out is that when you do run the numbers in the first part of the problem, when you caught the ball, if you run these numbers, you get a velocity that's actually less than the velocity if you don't catch the ball. In other words, if you catch the ball and y'all move together, your system is going to be moving at a slower speed than you would be if the ball bounced off of you. And this is because the total change in momentum for the second part is greater. You can probably reason your way through why that's the case. If you can't, I welcome you to come talk to me. But if you look at the total change in momentum, in this case, it has to be greater because one of the momenta is in effect reversing direction. That's sort of a crude explanation, but the idea is there's a greater change in momentum here, so it all works out to where you are actually moving at a faster velocity. There's a great demo about this called a ballistic pendulum, where you can either stick an object to a pendulum or bounce an object off of a pendulum, which we'll look at in lab this week or next week.